Okay, dear colleagues, let us start our BIMS Integrable System seminar. And today our speaker is Kun Zhang from NVU, and his talk about Yang-Baxter gates and integrable circuits.
Okay. Yeah, let me begin. Yes, thanks for the invitation. Today I'm going to talk about our research about this Yang-Baxter gates and the integrable circuits. So these following two works here, the arXiv file, are collaborated with Professor Kun Zhang and also Professor Yang Li, also from Northwest University, and Kwangming Yu, he's from Brookhaven National Lab, and Professor Vladimir Korepin, he's from YTP. Yeah, this YTP is from United States, not the YTP from Japan, the Yang Institute of Theoretical Physics. Okay, so I'm going to talk about the following sections. So first is a background. So this subject is a combined research about quantum computation and the integrable system. So I think people from integrable system know the Yang-Baxter equation very well. This is a central subject in the quantum integrable system. And another research is about quantum computation. Quantum computation is kind of technology, but also people thinking like the dynamics of quantum system in the viewpoint of computation. There is a model, so-called quantum circuit model. So this is the most natural computational model for the quantum computation. Yeah, I will introduce later. So in these two subjects, the Yang-Baxter equation, and in the context of quantum circuit model, we have the so-called Yang-Baxter gates. So this is the one central subject in these two research directions. So some background about the quantum circuit model. So quantum computation and the classical computation, they share the basic logic. So we have some initial state or initial bits, and doing some computation means doing some operations like doing the NOT gate, doing the control gate. So in the quantum computation, it's similar. We have some initial qubits. Usually, is all zero state. So the qubits is a quantum two-level system. So quantum binary digits. So the difference between quantum computation and classical computation is we use the quantum operation to control the qubits. So the quantum operation means the evolution is from the Schrödinger equation. The solution of Schrödinger equation is basically a unitary operator. So for the n qubits, you can say like the quantum gates is a large unitary evolution operator. And in the context of quantum computation, for the computer, we don't realize a very big evolution operator. Instead, we decompose the evolution operator into the single qubit gate and a two-qubit gate. So we're doing some logical operations like a single qubit operation, two-qubit operation, and combined together, we have a final state. And we measure the final state, get some distributions, or get one state. And this state is a solution of the computational task. So this is a little bit of introduction about the quantum circuit model. And another topic, I think the audience, most people are from the integrable system. So we all know like the Yang-Baxter equation plays a central role of the integrable models. So here the Yang-Baxter equation, you can think of the Yang-Baxter equation as a two-body scattering matrix, and this is a consistent relation about the decomposition of three-body scattering matrix into the two-body scattering matrix, and the order does not matter. So we have this consistent relation. But also we can think the two-body scattering matrix as a two-qubit evolution. So we can put the R matrix as a gate. So we use a box as a quantum operation, and also we use the braid notation, like vertex notation here means this is a topological operation, and the Yang-Baxter equation in the quantum circuit model is in this picture. Of course, the Yang-Baxter equation has a spectrum parameters, but in the special case, like for example, in this spectrum, if the spectrum parameter mu here equals to 0, we go back to the topological braid group relation. And the people, mathematicians study the relationship between the braid group relation and also the Yang-Baxter equation. They share some basic structure. So a more background about the Yang-Baxter gate. So the Yang-Baxter gate is so the first introduced in the quantum computation is the braid gate. Yeah, because people thinking like you can using the topological operation, and this topological operation is a representation of the braid group. So this is so-called topological quantum computing. They have some fault-tolerant properties introduced by Bethe, Freeman, and Wang Zhenhan. And later, I think the major researcher is Kaufman. Kaufman is a mathematician. He introduced the braid group relation into the study of quantum information. So the braid group relation, the braid group characterizes the low-dimensional topological invariants. They want to introduce the braid group relation to study the quantum entanglement. Yeah, but this subject is not successful because quantum entanglement is much more complicated compared to the nodes and the braids. So I think until 2017, Prosen and other people introduced the Yang-Baxter gate into the quantum circuit model. So basically, they find like the quantum circuit composed of the Yang-Baxter gate are also integrable. It means like the evolution is discretized. Yeah, later I will explain in details. And also in the context of the stellar automaton, people studying the integrability of the stellar automaton in the context of Yang-Baxter integrability. I think Postguy did a lot of wonderful research in this subject. And in experiments, people using the quantum computers to study the non-equilibrium dynamics, and the integrable circuit represents the non-equilibrium dynamics of the integrable system. So now I gave a specific example, and yeah, everyone knows the XX model, the most classical example of quantum integrable system. So we have this Hamiltonia given by the Pauli matrix, and the evolution is given by the exponential of this Hamiltonia. So as I explained before, so quantum computer cannot realize this operation because the operation on the quantum computers are only single and two-qubit gates. So you have to decompose this evolution into the basic 1 or 2-qubit gates. So one method is using the Toronto formula. So you can decompose the Hamiltonia into two parts. One part is this Pauli matrix is acting on the even outside, and the second is this Pauli matrix acting on the odd even side. Like one step change the qubit side. So you can decompose this Hamiltonia into two parts, and these two parts you're acting only on the even side or acting on the outside. These two parts commute, so you can just divide the Hamiltonia into these two parts. The H even and H out does not commute, but every term in the H even they commute because they're acting on the different side. They do not have overlap. So H even is Pauli term which are commutative, and all H odd are Pauli term which are commutative. But H even and H odd does not commute. So it introduce some errors if you realize the h-x in this way. There are some commuters here. But if you divide the time step with n, if n is very large, and you take the limit, the errors is a high order in terms of t over n. So it goes back to the original evolution. So this is the idea of decompose the evolution of the integrable system into basic units of single and two-qubit gates. And in fact, this building block, this two-qubit evolution, this is R matrix of the XX model. Yeah, but maybe this notation is similar with R matrix of the XX model, but you have to put the normalization here to make this R matrix unit to make this R matrix unitary. Because the only requirement for the quantum gate is unitary. So every unitary matrix can be viewed as quantum gates. So in conclusion, the total circuit is decomposed evolution into the basic two-qubit gates, and you divide the term which do not commute. And the total circuit of XX model is R matrix acting on the adjacent two-qubit gates, and you have two layers of the circuit here. So here is more clearly in the quantum circuit diagram. So you have the R matrix acting on the first and the second qubits, and so in the first layer, on the starting is the even side, and they do not commute. So you can put them together, and they commute. And as for the second layer, this is they acting on the outside, and we assume the theoretical boundary condition. Yeah, of course, we can generalize later to the open boundary condition. And so the repeating units is this the even and odd sides. So the repeating units is only two layers of the R matrix. So basically, the total circuit is repeating these two layers of the gates here, and if you think the n is large, so the delta is small, and the n is large, you go back to the original evolution of the XX model. And in the 2017, Proser and his colleagues shows this circuit is Yang-Baxter integrable. In that paper, they show, yeah, they can construct the transfer matrix. So the standard method, the standard algebraic Bethe ansatz can apply. So they construct this R matrix with inhomogeneous parameter here. So the R matrix is not homogeneous because this minus sign here. So basically the transfer matrix is R minus R plus, R minus R plus. And the trick is this transfer matrix. If you're taking the so the lambda is a spectrum parameter. If you're taking the special value of the spectrum parameter, for example, if you're taking the lambda equals to delta, so this is R delta, and for the next point, it goes to 0 because this is inhomogeneous, minus sign, plus sign, minus sign, plus sign. So in the special point, this special point lambda, the transfer matrix is in fact one layer of the circuit. So here, so the lambda equals to delta. This is the quantum circuit on the even side, and if you have the minus delta, and you have the here minus delta here, so the minus delta, R minus delta equals to R dagger delta. So you have the dagger here, but you can construct these two terms together. So here, this is the third line. The transfer matrix inverse at the point minus 2 delta over 2 times the transfer matrix at the point delta over 2. Sorry, maybe there is a typo. There should be no 2 here. But anyway, you can construct the basic units of the integrable circuit from the transfer matrix. So the evolution commutes with the transfer matrix. So the evolution is integrable. So that's the basic idea behind the integrable circuit. And one feature about the integrable circuit is they have the infinite number of conserved charges. So the standard method also works for the integrable circuit. So you take the logarithm derivative, you get the conserved charge. This is the one example. If n equals to 1, and you take the first order logarithm derivative at the special point, you have you give 2 charges. Yeah, because in the staggered transfer matrix, you have 2 points. And you can find the original 2 local conserved charge. In fact, are 3 local terms here. There are 2 additional terms compared to the XX model. Yeah, because the first logarithm derivative in the XX model gives you the Hamiltonian density. But for the integrable circuit, you have additional 2 terms here. But you can verify if the delta goes to 0, means the total step, means the small n goes to the large, and these 2 terms vanish, and it go back to the original XX model. So this is the one special point about the integrable XX circuit and the integrable XX model. The people from Japan, they verify this conserved charge on the quantum computers. Of course, conserved charge means this quantity is a constant under the evolution of the circuit. But however, because quantum computers are not ideal, there are many errors and noises, and so you can see the conserved charge is kind of decay. Here, for each line, is the value of conserved charge with the number of the evolution's depths. So the d is the small n before. You have 1 layer, means you have just 1 layer of odd side, 1 layer of even side, and through the evolution, the conserved charge goes to 0. It's kind of decay because the noisy quantum computer. So the ideal value is a dot line. And in fact, this is a popular subject in recent days, and people from Google, people from IBM, they all realize the integrable circuit on the quantum computers. The reason why they're interested, because they want to study the integrable breaking dynamics. So this regime, you do not have the well-defined, well-controlled dynamics. You do not have analytical results. So people want to study the properties of the integrable breaking dynamics. But at the beginning, they always realize the integrable circuit first, and they introduce some parameters, introduce some additional terms, break the integrability. For example, in last year, IBM studied the summarization of the integrable circuit because the conserved charge integrable system does not summarize. So IBM first show like the integrable system does not follow the standard summarization, and but when they break the integrability, it's going to summarize as a regular chaotic system. So this is more popular in the experimental part. So my second part is talking about this Yang-Baxter gate. So this is we get some properties of the Yang-Baxter gate. First, some background about the quantum gates. So the only requirement for the quantum gates are unitary. So every unitary matrix can be viewed as a quantum operation. But one special point is people prove like any unitary matrix you can construct from the single and 2-qubit gates. But for the classical computation, 1 and 2-bit gate are not enough. You also need a 3-bit gate. So this is one essential difference from the quantum and the classical computation. And the third point is any two-qubit gate can generate a quantum entanglement, can generate some quantum correlations. They can construct any unitary matrix with a single qubit gates. So this concept is called the universal quantum gate. Quantum gate. It means universal means you can construct any other unitary evolution from these two-qubit and single qubit gates. And the most popular or standard evolution in quantum computation is this CNOT gate. So this is a control operation. If the first qubit is 0, you do nothing, and the first qubit is 1, you do a poly X. You change the qubit size. And of course, this is a computational language. So this you can see this is not natural in the physics viewpoint because the Hamiltonian of CNOT is complicated. There's no easy Hamiltonian behind this CNOT operation. But of course, if you think the poly X interaction, you get this so-called RZZ gate. This is more natural for the physical quantum computer. Standard result about two-qubit gates is this element of SU2 group. You can decompose into the SU2, and you can decompose into the SU2 part. And what's left is the so-called non-local part of the SU2 elements. And there are three parameters characterize these non-local properties. So this decomposition becomes very useful because any two-qubit gates with the same A1, A2, A3 means they can convert it from the single qubit gates. It means they can generate the same kind of quantum entanglement. So this A1, A2, A3 are generally the parameters of two-qubit gates. Another concept is the so-called entanglement power. It characterizes the ability of entanglement generation from the two-qubit gates. So basically, you're acting on this U gate on any product state, and you calculate the linear entropy and take the average of every single qubit gate here. If this value is large, it means this two-qubit gate can generate large entanglement. If this value is small, it means this two-qubit gate cannot generate large entanglement. And this quantity can be analytically calculated. So given by the A1, A2, A3 parameters here. So you only need 3 parameters to characterize the two-qubit gates. So in the geometric picture, so you can think every two-qubit gates is on the point of a tetrahedron. So this O, A1, A2, A3 here, and C0 is in the middle. For example, A3 point means pi over 2, pi over 2, pi over 2. And this point is a swap operation, also the permutation. So permutation, you cannot generate quantum entanglement from permutation. So at this point, the entanglement power of the permutation is 0. But C0 can generate entanglement. The one theorem about this geometric picture is to decompose any so you basically from the geometric understanding, any two-qubit gates in the tetrahedron, you can find the minimum number of constructing of this two-qubit gate from other two-qubit gates. So the one universal theory is any two-qubit gates with non-local parameters A1, A2, A3. If you want to use the RZZ gate to construct this U, the number of RZZ you needed is in the regime of the it's larger than the A1, A2, A3 divided by theta. So in a special case, so it means like every two-qubit gates can be decomposed into 3 CNOTs, at most 3 CNOTs here. And another property is if the two parameters follow this relations, they can generate the Bell state. They can generate the maximal entangled states. And I go back to subject of the braid group. Braid group is a simplified version of the Yang-Baxter equation. There's no spectrum parameters here, and so the braid group or braid gate is a 4x4 matrix, and all the solution of this 4x4 matrix are known from very long time ago. So we can view this unitary 4x4 solution as a braid gate. So this is four families of the braid gates, and of course there are other families, but they can convert into these four families from single qubit gate operations. And the phi here is braid gate parameters, and they can take any value. For example, the B1 is a kind of permutation, but with phase phi 2, phi 3 here. And we calculated the non-local parameters here. We find the braid group is only here on the two-qubit tetrahedron. So you can see the braid group, the B1, B2, B3, these three families are only here, and the B4 is here. So if you remember, the B4 is also C0. It means like B4 is equivalent to the C0 gate. And other point, you do not have the braid group, braid gate here. So it basically means the braid so the braid relation is more complicated. Sorry, the two-qubit entanglement is more complicated compared to the braid relation. For example, two-qubit gates from here is not equivalent to a braid relation. So you cannot characterize this entanglement properties with a topological braid operator. So that's the reason why this direction is unsuccessful, because quantum entanglement is more complicated compared to the low-dimensional topological entanglement. So this is some details. So based on the geometric representation, we find the optimal decomposition. So decompose the B1, B2, B3 into the minimum number of the C0 gate here. So this is some details. Maybe I can skip here. So our main subject is Yang-Baxter gate. So there is a standard procedure to generate the solution of Yang-Baxter equation from the braid operation or braid operator. So you simply replace the eigenvalue of the braid operator with the polynomial of the spectrum parameters. So this is a procedure of replacing the eigenvalue of the braid operator with some polynomial of the spectrum parameters. So basically, you introduce the spectrum parameter from the eigenvalue of the braid group. Of course, if there are only two eigenvalues, you only have this way to generate the Yang-Baxter generate the R matrix. But if there are three different eigenvalues, you have different methods, because you can permute the three different eigenvalues here. So it implies one braid operator, you can generate a different R matrix. So we calculated the R matrix from the B1, B2, B3, and B4. For the B1, we get three family of R gates. So the first one is more familiar because this is XXZ R matrix. And these two are more uncommon because it looks like a 6-vertex model, but the diagonal term in the submatrix are 0 here. So this is the first type of the Yang-Baxter gates. Similar, we have the second one. And these three are not common in the context of integrable system. And for the B3, it's more complicated. But the R3 are all from the 8-vertex model. And the last, the R4. R4 is more simple. Is a simple 8-vertex model. And the B4 only have two eigenvalues, so you only have one R matrix from B4. In the geometric picture, we just find the non-local parameters of this Yang-Baxter gate. We find that the Yang-Baxter gate only exists on the edge of A2, A3, on the edge of O A1 and only these two faces. In other place, there are no Yang-Baxter gates. So we conjecture the Yang-Baxter gate is only on the surface of the tetrahedron. But more deep reasons, we don't know. We just calculate the number of parameters to see where they exist, the Yang-Baxter gate. I think the Yang-Baxter relation, operator relation, forbid the two-qubit gates go inside the two-qubit tetrahedron. And more details is based on the geometric picture. We find the gate decomposition, the optimal gate decomposition in terms of the first kind of Yang-Baxter gate, and also the second or the third Yang-Baxter gate decomposition. So this is more technical. But anyway, so based on the geometric picture, we can analyze the decomposition and prove this is the optimal. The optimal means we use the least number of CNOTs. It means, for example, in this case, we can not construct this R matrix with two CNOTs. So the three CNOT is the least number. Another interesting is the entangling power of the R matrix. So the spectrum parameter. So basically, spectrum parameters is the evolution time of this Hamiltonian. So you can expect increasing the spectrum parameters, the entanglement becomes large. But also this phi does not come from the spectrum parameter. It's more like a Q deformation of the R matrix. Also can change the entanglement of the R matrix, and it's more like it's more like this spectrum parameter eta and also the braid parameter phi combined together to determine to decide the entanglement generation of the R matrix or R gate. So for my last part of the talk, I will talk about some recent results from some generalization of the integrable circuit. I think last week, Mizuki talked about the construction of the conserved quantities for the spin chain, for the spin 1 half or for the spin 1. But however, the definition of the quantum integrability is a not well-defined concept. For example, I think most people agree like a quantum integrable system is a model which have infinite number of local conserved quantities. This is one common feature, but this is not unique. For example, people also think like the integrable system means we can exactly solve mainly from the Bethe ansatz method. So this is more specific called Yang-Baxter integrable. And another definition, people from the random matrix theory, people think like the eigenvalue distribution can distinguish the integrable or chaotic system. In general, the integrable system, because they have the conserved quantities, they do not have the level repulsion. It means like the level statistic, the space between different levels can come close as close as possible. And the fourth one, of course, this is also the feature of Yang-Baxter integrable. It means the scattering matrix is two-body reducible. It means you can decompose the scattering matrix into the two-body scattering matrix. Anyway, so the definition is not unique. So if we want to study the generalization of the integrable circuit, but however, if the original Bethe ansatz method does not work, so which quantity should we look? So we're working on the conserved charge. Of course, this is the one analytical result here. But later I will show more straightforward numerical calculation to show like the Yang-Baxter circuit has this Poisson level distribution. So before I talk about this toroidal circuit, but in fact, this is only one special decomposition of the evolution operator into the non-commutative parts. For example, you have the Hamiltonia, and you can divide it into k parts. Each part is in each part they commute. Sorry, maybe this is a typo. So in the original XX model, so we decompose into two parts. One part is the even side operation. The other part is odd side operation. These two parts do not commute, but inside each part, they all commute. So you can just approximate the evolution operator of this Hamiltonia into the product of the divided Hamiltonia. But of course, there are errors. If you simply just multiply these two together, you have the arrow scaling as 2 square. So this is the first order decomposition. But you go to the higher orders, you can construct some non-trivial sequences to cancel the higher order terms. And so this is so-called Suzuki total decomposition. So this is yeah, later I will show the meaning of this diagram. So diagram of this operation. So originally we only talk about, so the present paper talk about the total decomposition in the first order. So we only have the even odd side and repeating these units. But for the second order, if we apply the Suzuki total decomposition, so the repeating unit becomes the even odd even, and the spectrum parameter becomes delta over 2, and the middle one is delta, and again delta over 2. So the repeating units is 3 layers of the circuit. So this is the second order. And if you go to the higher order, it becomes more complicated. For example, in the first order, the repeating unit is this large operator. So this operator has even, odd, even, odd, even, odd, even, odd. They have 11 layers, and each layer they may have different parameters here. So in this case, the spectrum parameters, so the parameters in the R matrix is P2 times delta over 2. And the second one becomes P2 delta. And the middle one is like 1 minus 3 P2. And P2 is an irrational number. So as you can see, the second order circuit, the repeating unit is this even, odd, even. And the middle one has parameters delta, and the first and the third layer, the parameter is delta over 2. For the higher order, so this diagram become more complicated. I do not draw the diagram here. But anyway, so our conjecture is this: all order toward circuit should be integrable because they come from the evolution of the integrable system. For example, in the second order, this repeating unit is even, odd, even. So this is also integrable because basically you can generate the repeating unit from the transfer matrix. So this is a trivial generalization. The hard point is how to construct this transfer matrix of the higher order decomposition. So right now we are not successful yet, but we are working on this direction. The reason why the standard Bayes ansatz does not work because in the higher order, you can see the higher order circuit, the spectrum parameters are different here. This is P2 over 2, but the middle one becomes 1 minus 3 P2 over 2. So basically, you need 2 transfer matrix with 2 inhomogeneous parameters, but the transfer matrix with different inhomogeneous does not have the RTT relation. So basically, if you construct the transfer matrix from 2 homogeneous parameters, they do not commute. So means some integrable breaking. But numerically, we verified the level statics. So maybe just more details. So consider the Hamiltonia. You can find the eigenvalues, all the non-degenerate eigenvalues of this Hamiltonia. and you calculate the level spacings, just the first gap of the ground state and the first excited state, and the third one is the gap between the second excited state and the first excited state. So you find the level spacings, and you consider the level spacings as random variables, and you can find the distribution of these random variables. If these random variables is like a Poisson distribution, it's one feature about the integral system. Is this distribution more like Gaussian? It means there are level repulsions. It means like the level will not go, so the level spacing will not go to zero in the thermodynamic limit. So the most special case, we consider the Yang-Baxter circuit with random spectrum parameter. So in this circuit, we consider the R matrix and each R matrix with a different random numbers here. Basically, we generated the delta from random number, and we calculated the level spacing or the level distribution. So this is follow the standard Poisson distribution, and in fact, this result does not dependent on how you generated this random number. Because if you choose the Gaussian, if you choose the even random number, they all give you this level spacing, the Poisson level spacing. But the hard point is how you can find the conserved quantity from this random R circuit. I think last week Mizuki gave one example. Probably their method also works here, but we are not sure yet. We're working on this XX model yet. Because X model, the R matrix is simply the exponential of XX, YY, ZZ. So everything also polymatrix, and you can start with the computation of the polymatrix and working out the conserved quantities. So this is possible. Yeah, but anyway, so this is one surprising, because from the random matrix theory, if the matrix elements are some random numbers, usually goes to the Gaussian distribution. But here we choose the random numbers, but we fix the structure of the but we fix the building block of the matrix as the R matrix. So it's not breaks the integrability from the viewpoint of level statistics. So anyway, so this is the one possible generalizations here. Okay, maybe go to one quick conclusion. So the Yang-Baxter gate is a building block of the integrable circuit. People already prove like if every circuit from the Yang-Baxter gates with the same spectrum parameters, they are integrable. But the people do not prove such as random parameters or other parameters chosen, like the circuit is integrable or not. But our conjecture is any Yang-Baxter circuits without any specification of the spectrum parameters may still is integrable. So our one main result from our research is we try to study the properties of the Yang-Baxter gates, and from the viewpoint of the two-qubit geometric picture, we can find the optimal constructions and also the position of the Yang-Baxter gate. And the Yang-Baxter gates are only exist on some regions of the two-qubit tetrahedron, and other point they do not have the Yang-Baxter gates. And one possible generalization is the higher order toroidal circuits maybe also integrable. Yeah, because the higher order toroidal circuit also comes from the dynamics of the integrable system. But how to construct the transfer matrix is one major difficulty. And anyway, we numerically verify the level statistics of the random Yang-Baxter circuit, and surprising, this random circuit also follow the Poisson distribution. maybe one more general outlook. So the general motivation behind the study of combining the quantum computation and the integrable system maybe more fundamental than people think. Because as I mentioned, some people think the one sufficient condition for the integrable means the scattering matrix is two-body reducible. But also from the quantum circuit model, you can see the quantum circuit is also composed with single and two-qubit gates. You do not need three-qubit gates. So basically, you only need two-qubit gates to construct any operation you want. So the quantum circuit model is a more generalized factorized scattering matrix. But of course, any operator is not integrable. But maybe we can find some patterns of the quantum circuit model to study the integrability. So people think this quantum circuit model has a deep connection with the quantum integrable system because the scattering matrix are in these two cases, the scattering matrix are all factorized. And one relation here. So people already show the Theor circuit, the first order Theor circuit of Yang-Baxter integrable system. So the building block is the Yang-Baxter gate. These are integrable circuit. But you can go to some generalization because in the Theor circuit, the parameters you need to choose like a first order Theor circuit. The parameters you have to choose all the same. But our conjecture is like a Yang-Baxter circuit with other different spectrum parameters. They are also integrable. So the IC may be a larger set of TC-IC. And the third point is from the dynamical viewpoint. So because the conserved quantity, the information spreading or the scrambling of the integrable circuit is limited. So maybe so we know the integrability means the information scrambling limited, but not all the limited information scrambling limited circuits are integrable. So maybe this set is larger compared to the IC or TCS. And the fourth point is all the circuit from the physical system means all the simulation circuit of the physical system. So this is more larger set compared to the integrable system. So one interesting question is more like complexity theory. So how you categorize different kinds of circuit. So maybe one conjecture is you have the integrable circuit in the middle because this is the more special point. But you go into other circuit and the dynamics such as scrambling limited is a larger class, and the simulation of quantum circuit. Quantum system is a more larger set, and the rest is other quantum circuit, which of course not integrable. So that's the more reason to study the relationship between the integrable system and the quantum circuit model. I think that's all my talk here. Okay, thank you.
Okay, thank you for your talk. Questions? Okay, let me ask you, could you please comment what is your expected integrability for your higher approximation? Because you said that it is not RTT, so which integrability you expected here?
The Yang-Baxter integrable. So basically, we want to construct the R matrix, which describe this higher order decomposition. So the first order here is simple because you only need one inhomogeneous parameter in the transfer matrix. You can construct the R matrix of this first order Theor circuit. But for the higher order, the spectrum parameters becomes complicated. So you need different R R matrix, but different R matrix. Sorry, you need different transfer matrix, but different transfer matrix they do not commute. So the RTT relation does not hold for. So what I mean here is the RT. The middle T is one inhomogeneous parameter, and the third one is another inhomogeneous parameter. So this RTT does not equal to TTR. So the standard Bayes ansatz method does not work.
Yeah, but do you expect it can be modified somehow?
Yeah, we expect, but we don't know how. We are working on maybe some nested construction. We're not sure yet. Yeah, but this is one interpretation because the higher order also come from the XX model. So the dynamics is all similar with XX model. So you expect every integrable dynamics of the higher order circuit. So it should be integrable anyway.
Okay, thank you. More questions? Okay, if not, let's send our speaker again.
Okay, thank you.